Hello, my name is Varat, and we are the second group working with Isha. Full screen. That's why is it not full screen? Okay, that's okay. Okay, that's okay. Yeah. The tentative title for our project is Frequency Selective Reweighting for Stable Voice Synthesis using Wavelet Decomposition. I'll just talk quickly a little bit about the presentation flow. We'll first talk a little bit about what diffusion models are, very short intro, just to lay context for the presentation. Then we'll talk about the first paper, which is about moving average sampling in frequency domain. So that paper was based on image models, so diffusion-based image generation. And we take inspiration from we take inspiration of the idea, which they applied on images, and we'll apply those ideas for a text-to-speech model, and that is a flow matching model instead of the diffusion model. So to quickly summarize the idea, what we'll be doing is our TTS text-to-speech model will generate MEL spectrograms, and we'll perform a DWT decomposition on the MEL spectrogram, and depending and according to the claim that we'll prove at the end of the presentation, we'll do some smart frequency selective reweighting on the components on the different subbands of the MEL spectrogram, and then we'll feed that back into the TTS, so that it generates a more stabler output. So that's the idea. Just to give
So
some.
you'll do away with MEL altogether.
No, we'll work with MEL.
So how will you have MEL and wave?
So we'll take the MEL spectrogram and we'll perform a DWT on the MEL spectrogram. We'll do the reweighting in the DWT domain and then take the IDWT. So we have the MEL spectrogram again. So
is there any way we can bypass MEL? I mean, if you're adding more.
That takes a lot of acoustic and the venting and all from. It's better to go.
Generation happens in MEL.
That I understand, but I'm just saying, aren't we adding a layer of overhead here?
Directly applying to the.
Sorry, yeah.
MEL actually is a representative of the frequency bin, so I think there they want to play with the frequency.
But you're dealing with two different frequencies.
Yes, we get the joint sense of frequency and
we are dealing with the frequency of the frequency band.
the approximation and detail.
There'll be a little mind.
Yes, yes. Yes, sir. We are considering normalization techniques also. We'll talk about it. So this is just to lay some background about what a DDPM model is. So just quickly, there is a forward process and there is a reverse process. So forward process is Markovian and the noise is progressively added to your ground truth. And in the reverse process, we try to reconstruct the original sample from the noise. So this is just some mathematical formulation for the same. So xt is what what we have, and x0 is the ground truth. And you can see that the noise is just Gaussian, added at every step, small increments of noise. And the neural network is essentially approximating, so it's xt minus 1 from t, because we're going in the reverse direction. And we try to get that successively. And the loss function is defined, so it's scale divergence because it is the distance between two probability distributions. So one is the ground truth probability distribution and the other one is what our neural network is approximating. So that's just the scale divergence. Yes, so DDPM, so DDPM has some limitations. So denoising is happening only on the basis of just the previous sample. And therefore the process is slow, it takes a lot of iterations. The idea of a DDIM is to, so if you look at this equation, so this equation is just a generalization of what the DDPM can do. What the DDPM suggests is to make this eta t equal to 0, and then the whole process becomes non-Markovian. And because it becomes non-Markovian and eta t is 0, we can clearly see it becomes deterministic, and then we can just speed through the entire process. So that is what DDPM proposes to achieve. It speeds up the denoising process compared to DDPM. So that's just the broad theme for the paper that we'll talk about next. So the paper that we'll talk about next, moving average sampling in frequency domain, works on images and with the DDIM model. So that was the background for the paper.
Slide change already. So the first paper is titled MASF, which stands for Moving Average Sampling in Frequency Domain. So here is an example showing the denoising of a pixel value for an image. The blue curve represents the ground truth values that we have from the forward process of the diffusion model. The orange curve represents the denoising process. So as we can see that at each time step we see some errors at any time step, and the problem is that these errors can accumulate over time, resulting in something entirely different from the ground truth value. So this leads to the instability in the diffusion model. Now, what the paper proposes is that it says we can have a training-free approach using moving average to sort of stabilize this change from one sample to the next. Here is an example of the denoising process. So we start with a random Gaussian image, and then we successively remove noise from it to get something that makes sense. So we want to propose, the paper proposes to use moving average technique, but since these samples inherently comes from different data distributions, we cannot directly apply moving average to them. So what we do is that we project or map these distributions to some common distribution, which is in our case x naught t. So then we perform the moving average on this x naught t. So now the updated sample is simply the convex combination of the current sample and the moving average of the samples that we have seen so far. Also, one more observation is that different parts of the image tend to evolve differently. So, for example, in these two consecutive time steps, we see that the face of the cat evolves more sharply than, let's say, some other part of the image, like this left bottom corner of the image. So what the paper does is that it introduces a weight matrix which is the same size as the image. So this is going to control the different parts of the image. So for example, if the face of the cat is changing a lot in these two successive time steps, it's going to have a higher value for these part of the image, such that gamma WT is a higher value, and hence we are relying more on the global average to update our sample, which is x naught t. Yeah. Yeah. So, so far we have been doing the moving average thing in the pixel space. Now we want to extend the same thing into the frequency domain. So to decompose the image into its frequency components, we use DWT, which is discrete wavelet transform. So DWT basically decomposes this image into its 4 frequency subbands. This is LL, LH, HL, and HH. LL represents the low frequency components of the image, and these 3 represents the high frequency components of the image. And this is the equivalent equation to modify or get the updated subbands in the frequency domain. So we just simply replace them by the bands and the corresponding weight matrices. Then we also observe one more thing, that low frequency components of the image tend to stabilize or evolve faster and before the high frequency components. So based on this, the paper introduces one more parameter or factor called beta, which just boosts the denoising of low frequency components earlier in the process and the high frequency component later in the process. Yeah.
That's by definition of low frequency.
Yes.
So why are they trying to? What are they trying to do? Not clear. So
beta is going to start with a higher value for low frequency components, and then linearly reduce to a smaller value as we progress in the denoising process. So basically, they are focusing more on the low.
Why? I mean,
the premise is that, as we shown in the previous past transformation and the detailed forms of payments that are different rates. The low pass segment and the high space from the shell HH and LH. The problem is all those errors that we showed in the first plot has been demonstrated by the MASF paper, that they happen because these different bands develop at different rates. So let's say you have LL band that is saturated with its development. Now you run another iteration that develops the LH band. So that development also makes some changes in the LL band. And then another iteration will be needed to stabilize it. That will create some disturbance in stitch bandwidth. So that's the whole part where different path of frequency bands develop at different rates, it will take longer for the denoising process to stabilize. That's the whole principle.
So the idea is that if we can stabilize them early or do it in fewer iterations.
That's basically putting a prior.
Sort of. But it is adapting.
The D beta.
Yes. So for low frequency components, it reduces from some higher value to a lower to a smaller value linearly. So finally, we perform the inverse discrete value transform to get the sample back in the image space, and then we can just carry on with the denoising. So this is the overall framework of what we have discussed so far. So we begin with a noisy image. Let's say we are at some time t with xt. We predict the noise from a diffusion model, use this noise and xt to get x naught t in the data space. Then we perform discrete Wavelet transform to get the frequency subbands, perform the moving average, get the image back, updated sample x naught t, which is used to predict the next samples or to get the next samples, and the process carry on until we have x naught. And for the results, the metric that we are using is FID, and yeah, okay, sure. Yeah, sure. I mean, this gives better results than the original model. Yeah.
FID score is better for the lower iterations. There is a 2x gain in the FID score. Yeah.
So from here we move forward to FFTDS. It's a very recent paper. So FFTDS is a flow-based voice synthesis text-to-speech model. So I'll just briefly discuss what flow matching is. So we start with some velocity field, let's say UT, and we are trying to learn a model VT such that it predicts a flow that goes from a noisy distribution, let's say standard normal distribution, and a noise sample from it to the respective target that we want. And for in this case, we are using Bell spectrogram as a target. The problem with flow matching is that this is the loss function. And the problem here is that we don't know how to move forward in the path to predict this probability distribution and the model. So what we do is in the training, we use something called conditional flow matching. We give a target is the X1, the spectrogram, and we start with X naught, that is just a noise sample from our initial distribution. And we say, okay, let's move in this direction and try to find the best path that goes there. And this psi t represents the optimal flow path. And yeah, so this is, if we substitute psi t here, this is the equation that we get, and this is the loss function for the conditional flow matching. The FFTDS has an architecture very similar to its predecessors like E2TTS and VoiceBox. The new novelty in it is that it uses a contour next V2 block and a DIT block instead of a transformer.
Why are they not using any moving average?
That's what we are trying to do.
That's what you.
Yes, that's
Your
where we
30
come in.
Okay, I don't want to steal it.
Yes. So the way MASF proposes things is that it's model agnostic, it's training agnostic. So we're not going to discuss about how the training works. Let's move towards the inference. What happens in the inference is we start with a sample noise X naught from some noisy distribution, and we try to obtain a flow where the end of it is our target spectrogram X1. We do it by solving a ODE, that is difference, the derivative of the flow should follow this path. That is basically what the model is. And that ODE is solved in n steps, n is basically the number of function evaluation, NFE. And this input, it takes input as the XREF, that is the reference spectrogram, acts as a style guide of how we want to infill our new speech as. And ZREF gen is basically concatenated reference input and the generated text. Basically, the character sequence of what has been given as the transcript for the previous spectrogram and what is the target generation text. And after solving the ODE, the model discards the initial spectrogram and retains the generation and passes into a vocoder. By default, it uses vocose and produces a speech signal out of it. Next. Now what our hypothesis is that F5TTS or any similar voice text-to-speech models use n-step ODE solution in a denoising process. The premise sounds very similar to what we heard for DDPM and DDIM. And now another similarity is DDPM, DDIM work with images, and we are working with MEL spectrogram, which are again 2D arrays. So in an analogous sense, they are treated very close to images in various scenarios. So we hypothesize that voice synthesis models like F5TTS, which despite following a flow-based approach, will have some sense of instability incorporated to it. Maybe different from DDIM, the workings, but there will be something. So we run an experiment to test our hypothesis out. Yes. So we have a MEL spectrogram generated out of the 5TTS. We actually get the whole series of MEL spectrograms from X0 to X1. And this is some intermediate MEL spectrogram that we have. We perform DWT decomposition of the spectrogram. We obtain approximation coefficient, LH, HL, and HH bands. All these 4 things correspond to different features out of the generation. The LL is the approximation, LH is the vertical features that separates different phonemes. The HL is horizontal features, which is separation between different frequency bands of the speech. The HH features are diagonal features, that is interrelated between these two. We evaluate the L2 norms of these features, and we actually obtain something really different from what DDIM had. In this case, LL norms keeps growing. It does not saturate what we saw earlier, but there is very different patterns in all these different parts. DLL keeps on going. HL has a slightly very lower value, but it still keeps on going. The LH part saturates and the HH part saturates. So they have different rate and growth. That was the premise of our problem. This was generated.
Can this kind of inspire of, besides the moving average, also kind of the beta T? Can this inspire a beta T as well?
Yes, exactly. How different components evaluate is evolve is basically how beta T adapts itself.
Okay.
So that is what we are trying to study, how different components evolve. So this was for using different reference audio files, different XREFs, but using same generation text. In next.
Just to add to what you were saying. Image bands capture vertical features.
Yes.
So what is the separation between phones very well, but not the separation
between frequencies. We run the experiment again, but this time we use different text for generation. We use different WAV files and different text for different WAV files. And actually the pattern remains same. That means this is inherent in the model. This is not something because of the experimental bias. Yes. Frequency keeps on increasing. Yes. But the frequency differences are harder to. This is basically the inherent uncertainty principle here. We can't separate the frequency. This is basically the statistical evaluation of the whole thing. We see that there is a clear pattern of increase and saturation and those things.
Sorry, what is this band here?
Which band?
Oh,
this is a standard deviation. Plus
this is so very consistent. But then there's a very large standard deviation with.
Because we use very different audio samples. So they are nowhere similar to any other sample. Next slide, please. Now the thing is, there is an issue with treating spectrogram as images. That is, images do not have inherent meaning of the pixel value. Like they can be linearly scaled. And image I and alpha I, where alpha is some constant, basically the same thing. That does not hold true with the spectrograms. They have a non-linear scale in the y direction and a linear scale in the time direction. So to account for it, what we tried to do is for the base case, we tried normalizing it between -1 to 1.
The really synthetic nature of MEL, that's why I asked in the beginning. I know, MEL captures many things that probably You can't directly get from raw audio, but I still feel somewhere there's some redundancy in this entire process of using MEL, which is very synthetic after all.
Depending on the work we want to do, we can just use
Ah.
those speech instead of whole pen.
Okay.
Okay, so
Try the same thing. Discrete tokens also.
we can certainly think about it.
You can try codec tokens.
Yeah.
But anyways,
So the other observation is that if we
yeah, question.
So DWT is basically fixed convolution with downsampling, right?
Sure.
So why we are not using CNN based values? Like instead of fixing the convolution values, we can use CNN based approaches, right?
what we so in our scenario, what we want is we break the base thing that we have, the null spectrogram, into approximation and detail parts. Just want to observe how approximation and details grow. We
And the
want-
model using
That is the key. Yeah.
Hmm.
Training free.
It's training. I'll continue. So we normalize this within -1 to 1, and what we observe is that LL still grows, but the detail coefficients tend to fall, which is, well, the whole problem with this is that linearly normalizing this spectrum will not work. It will give you a sense in terms of using MASF as an image tool, because now you're treating it like the normalized thing, but it will still not capture the relation between the frequency, because now it will be distorted. The linear scale will make it exponential in the actual power spectrum. So that's where our problem statement comes in, that how do we generalize this MASF technique into the domain of this MEL spectrogram? That is basically the whole problem we are going to deal with in our project. Yeah. Yes.
One quick demo.
Yeah, so this is good to see demo because see, all projects must target a paper submission. Ideally, NeurIPS, because NeurIPS is pretty much aligned with your submission deadlines, right?
Yeah, I'll reconnect it.
So it'll be good to see some progress even during a seminar, if not coherence. But what is not acceptable is completely disparate presentations with no story you are giving for your project. This is an opportunity for making an impact to your project, right? Go ahead.
Okay, so just a quick demo. We've already pushed our files to GitHub and we've downloaded it, and so we just took a fork of the F5 TTS library and we've already installed it in this particular runtime. I'll just import the files. So this voice files.zip is a set of recordings that we did on which we will test our model. So I'll just run this file now. So this file is going to run it's going to take the inference of the model on different inputs of the audio file and try to generate different outputs, different text outputs. We've set the NFE steps to 60 in this case for the F5 TTS model. Yes. We should try that. We will try that next. We have not tried that. She's saying that the F5 TTS, the weights for this particular model were trained on the US English. We are trying it on our English. So she's saying maybe you should try it on US English itself.
There's sample audio we have tried, and
right.
given actually similar thought.
Oh, right, yeah. Sample audio we tried, yeah. So it's just generating. It's not too much. It will finish executing in 3 minutes. So lesser, I think. The whole thing will take 3 minutes. The entire. Yeah, I think we'll summarize after this. Those slides we'll summarize. Yeah, it's done. Yeah. 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 So now it's generated all these, it's generated all the audios, and it's also dumped all the MEL spectrograms. We'll just read those MEL spectrograms again into an array, and this is where we perform the DWT on the consequent MEL spectrograms in the trajectory. Yes, yes, sir. So it's just generating for everything now, and we'll look at the statistical variation and the LL norms just after this, right after this. Yeah, I think that's done. And now we'll visualize the evolution of norms across different subbands. Yeah, as we showed in the presentation, so the LL subbands keep increasing. LH, which captures this variation across different phonemes, is well defined, but not HL. And HH is also seems to saturate. And this is the statistical variation. So we're just trying to prove that the problem exists here, and hopefully we'll be able to solve it. Yeah.
So basically, in our experiments, we see that there is a clear uncoordinated growth in the frequency components. That means there is a sense of instability inherent to the development feature. Yeah, yeah, that's basically it. So this is so the next step is trying to find a better normalization structure so that we can compare different MEL spectrograms relatively. Yes,
Yeah, this was good presentation.
thank you.
Thank you.
Okay.